This short video reviews the calculation, use, and interpretation of z-scores. When something follows the normal curve, this relationship between the standard deviation and that distribution of scores makes it easy to describe someone's results in a meaningful way using what's known as a z-score. In previous videos, we asked whether having a pet that weighed 2 kilograms above average was no big deal or wildly huge. We recognized that the answer to that question depended on the variability of the scores, with the standard deviation being a yardstick that we could use to measure just how big something is. Well, that's exactly what a z-score does. A z-score is simply any score minus the mean divided by the standard deviation. In other words, it's how many standard deviations a score is above or below the mean. You can think of it as how large of a difference did we see between the score and the average score relative to how large of a difference did we expect to see among our scores. When you're talking about a z-score for someone's result, it can be in reference to the sample mean and the sample standard deviation, x bar and s, or a population mean and the population standard deviation, if you know those. In this usage, it's okay. The key is that it's how many standard deviations the score is above or below the mean. Z-scores provide a very straightforward way to answer certain types of questions about scores if the data follow a normal distribution. Let's focus on two types of questions that you can answer pretty easily using z-scores, again, if the data are normally distributed. One type of question gets at things like, what's the percentage of scores that fall above or below some given result? Let's say that we scored 55 on a test, and the mean for the test was 50 with a standard deviation of 5. The z-score would be 1, indicating that the score was 1 standard deviation above the mean. So, what's the percentage of people who scored below a z-score of 1? Looking at the normal curve, we know that 68.26% of the scores are within 1 standard deviation of the mean, or between a z-score of -1 and +1. Because the normal curve is symmetric, we know that half of that must be between the mean, or a z-score of 0, and a z-score of 1, or 34.13%. Finally, again, because the normal curve is symmetric, half of the scores are below the mean. So if we put both of those together, we see that 84.13% of the people scored below a z-score of 1. What if we wanted to know the percentage of people that scored above a z-score of 1? Well, that's easy and fairly obvious, isn't it? If 84.13% are below a z-score of 1, then 100 minus 84.13%, or 15.87%, must have scored above a z-score of 1. Now, when I was much younger, we had to do a lot of this work by hand, using tables in the back of books where we'd look up z-scores and go through this exact process I just described. Fortunately, now you can do this directly on a calculator or in Excel or some other software where you just enter a z-score and it returns this type of information. Nevertheless, it can help with your understanding of z-scores and the standard deviation to directly see this relationship rather than just rely on a computer to pop out some number that you may not fully understand. So let's go through one more example before we move on. In this case, let's say we scored 80 and the mean was 100 with a standard deviation of 10. The z-score would now be -2, indicating that the score was 2 standard deviations below the mean. So what's the percentage of people who scored below a z-score of -2? Looking at the normal curve, we know that 95.44% of scores are within 2 standard deviations of the mean, or between a z-score of -2 and +2. That tells us that the difference between 100% and 95.44%, or 4.56%, must be either below a z-score of -2 or above a z-score of +2. Because the normal curve is symmetric, we also know that that 4.56% must be split evenly on each side. So the area below a z-score of -2 must be 2.28. In other words, 2.28% of the people scored below a z-score of -2. What if we wanted to know the percentage of people that scored above a z-score of -2? It's simply 100% minus 2.28%, or 97.72%. Now, the other type of question where we'll often use z-scores or other similar measures is when we want to know the percentage of cases that were either less extreme, or more often, the cases that were more extreme than something that we observed. Notice that when we say extreme, we're not just talking about being higher or lower. We're talking about how far something is from the mean. So, continuing with our last example, what's the percentage of cases that are more extreme relative to the mean than a z-score of -2? It may help to take a look at a figure. We just saw that 95.44% of the scores fall between a z-score of -2 and +2. These scores are less extreme than a z-score of -2. To calculate the percentage of scores that are more extreme, we simply calculate 100% minus 95.44%, or 4.56%. Again, as we can see here, when we say more extreme than a z-score of -2, we mean less than -2 or greater than +2. More extreme includes both tails of the distribution. We'll use the idea of results more extreme than something a lot with statistical tests. More on that later. But for now, this wraps up our discussion of the normal curve and z-scores. Okay? Take care.